Alright, today we will start with Unit 1.7, which is titled Energy, Work and Power. Wait, have I shared my screen?
We can't see it.
My bad, just a sec. Can you see it?
Yes.
Okay. So, Unit 1.7 is Energy, Work and Power, and we will be beginning with the topic of energy, and we will in that process of talking about energy we will include work. So first of all, what is energy, right? The book, unfortunately and oddly enough, doesn't give a clear definition for what energy is, right? So very simplistic definition of energy is the ability or the capacity. Here's the whiteboard. It is the ability or the capacity to to do work or cause change. Right? And so this ability could be in the form of exerting, or usually is in the form of exerting a force, to cause something to move or change. Right, and so we look at different forms of energy and how they are transferred and how they are put into work. And so energy and work are very closely related. In fact, they're so closely related that the SI unit for energy and work both is joules. With the symbol J. Now, to start off, right, we're going to talk about energy stores. So, energy, that ability to do something, is present in different substances, different objects. It's not chemistry. Different objects in various forms, right? And those forms, various forms, are called stores of energy, right? And examples are kinetic energy, gravitational potential energy, chemical, elastic, nuclear, electrostatic, internal or thermal energy. And so the book goes on to give certain examples. So you've got chemical energy, and that's the kind of energy in fossil fuels, right? And so fossil fuels are burned to release that energy. right, in food, and so foods are digested to release and utilize that energy. And so what basically happens is that chemical energy in fossil fuels or in foods, right, there's an energy transfer when they are utilized. So there's a transfer of energy, and so that chemical energy in fossil fuels, for example, such as the fuel in your car, the petrol in your car, that's a fossil fuel that is burnt in the engine, and that produces, right, motion in the motor, which turns the whole system, gets your wheels moving, which gets the car moving. And so the transfer is that the chemical energy, right, is transferred to kinetic energy. Right, and so what we learn from that, when we talk about other stores, is that energy is transferred from one store to another. So over here you had chemical, and then you had kinetic energy, which is another, right, form of energy store. And the kinetic energy can be transferred to another kind of energy, and then so on and so forth, right? So chemical energy is one example of an energy store. Since I've mentioned kinetic energy, that's the one I will talk about next. So it is the energy possessed by objects that are in motion. And the faster something is moving, the more kinetic energy it has. So an example of energy transfer happening over here is, for example, you're hammering a nail. Alright, so the movement of your hand, just a minute. So your hand, the movement of your hand, so the kinetic energy from your hand movement, right? When the hammer hits the nail, it causes the nail to move into the wall or the wood or wherever it is you're putting it in. And so, right, that is an energy transfer. In this case, kinetic to kinetic. There are other, heat is also there. If you touch the nail after hammering it, it will be slightly heated up. It will feel slightly warmer. There's also sound, right? But the main energy transfer is kinetic to kinetic. So it's kinetic energy to kinetic energy in this case. Again, the transfers of energy are not like singular, as I mentioned, right? It's not just kinetic energy. There's sound, there's heat, there's vibration on the surface of wherever you're hammering that nail. That's why I said the main energy transfer over here is kinetic to kinetic. Then you've got, you've got gravitational potential energy. And so this is the energy that an object possesses based on its position above the earth. Above the earth's surface. I say surface because that is where you would normally find objects, and it is obviously right under the influence where this happens when an object is within the gravitational field of a body. So it's under the influence or effect of a gravitational field. In this case, the Earth's. Right, you would also experience gravitational potential energy on the moon or any other planet that has gravity, or any other moon or satellite. Right, obviously that would differ as to what the gravitational field strength is of that satellite. And so the higher up the body is, the further away it is, right, above the Earth's surface, the more, the higher, the more the store of gravitational potential energy it would have. An example, right, is a mountain reservoir. Right, so this is holding water, and there are pipes leading down the mountain, and so when the water is released, right, it moves down, and so the energy transfer that you have is gravitational potential energy, in this case being converted to kinetic energy. Make sense?
Yes.
Any questions?
No.
Okay. What else do we have? We have elastic strain energy. So that's an energy store, and this is, because of the condition of an object, if it's stretched or compressed. So in both cases, right, so elasticity is not just about stretchability, it is also about compressibility. So in both cases, right, an object that is being stretched or is being compressed will have elastic strain energy. An example would be, right, the string of a bow. Right, it is pulled back and released, right, which moves the arrow, it shoots the arrow forward. And so over here, the kind of energy transfer you have is elastic strain energy to kinetic energy of the arrow. Right, so not only is the form of energy being changed in transfers, it is the energy is also being transferred from object to object. Then you've got electrostatic energy. And this is the energy in charged particles. Right, it is involved in electricity. Right, so it's right, an example electricity, and so this kind of energy can be transferred by an electric current. Right, so for example, you have an electric heater. Winter is near, winter is coming. Right, and so you have electrostatic energy being transferred to internal energy or thermal energy, heat. And finally, I believe what they've mentioned, right? So internal energy is next, since I mentioned that. It's also called thermal energy. And this is the form of energy, the energy store that is, as they, the words they use, is the final fate of all the other energy stores. Although I'm not mentioning it as the final one, it is the penultimate one. There's one left. Final fate of all energy stores. So I did mention, right, heat over here in the kinetic energy. Right, chemical energy, when fossil fuels are burned, they do produce heat. Right, heat is released from the foods you digest, and so that helps maintain your internal body environment, right, your body temperature. Right, elastic strain also, right, if you keep stretching and compressing, you might feel something getting warm. Electrostatic, so heat and electricity are very closely linked. Right? Something has electricity passing through it, there will be heat as well. And so, right, how is that the final fate? Well, unless the aim is to produce heat, that is the aim, that is, right, what you want. In energy transfers, a lot of energy is lost as heat. Thermal energy. Again, we use the word lost because in that scenario, thermal energy or heat is not something we want, but it is something that we're getting. Unless, like the example of the heater, right, heat is exactly what we want, and so we're getting it, and that's good. All right, the final form of energy store mentioned is nuclear energy, and that is the energy inside the nucleus of an atom. Squeeze that in on this page. So nuclear energy in nucleus of atoms, and there's like a lot of energy stored in the nucleus, right? It can be transferred to other energy stores. Through nuclear fission and fusion, which will come later when we talk about radiation and radioactivity. So, nuclear fission and fusion reactions, and both of these involve tinkering with the nucleus of atoms and tapping into the energy, the vast energy store, massive energy store in the nucleus, and trying to make good use of it. Now, with that, right, we've talked about energy transfers. We've given examples of energy transfers. There is a particular example that they've given in the book. So and so what they talk about is using a battery or a cell, whatever you prefer calling it. The reason it's called a battery over here and not a cell is so that it's not confused. Cell is a common term, right? And so it's not confused with in science as the biological cell. Although if you use in proper context, for example, you may see the battery of your laptop and it says lithium ion cell. And so based on the context, we know that obviously lithium ion cells are not biological. So, but still, the term battery is used. And so, there's chemical energy stored in batteries. So there's a chemical energy store in batteries, and that's connected to a circuit. So that is converted to electricity, and that causes a motor to move, the setup that they've shown and talked about. And so that is kinetic energy. And then what that motor does is that it pulls on a weight and lifts it. So in this case you have the kinetic energy of the motor being converted into gravitational potential energy of the weight. Then what they do is that they release the weight and so the gravitational potential energy is converted to kinetic energy again, and that kinetic energy is transferred to the movement of a generator, and that generator causes a right lamp to light up. Right, so generator moves, it causes the coil to move, it converts the kinetic energy, right? It lights up a lamp, and this is like, as you can realize, I'm like really summarizing it. It's given in text in the book, and so what's happening over here is the kinetic energy of the generator is being converted to internal energy of the lamp. And so that's just a demonstration of energy transfers, right? And what we realize from this is, in a system there are multiple transfers happening, and again, right, we're not even talking about the sound generated or the heat loss, right? So those are energy transfers happening as well, right? But we're just focusing on the main transfer, so we're not focusing on the loss of energy from the system, although that will be mentioned. Okay. So there are other examples of energy transfers. I'll just mention that. So the example given over here is electrical work happening. The topic of work is coming in. So all of this was electrical work. Right, but you can also have mechanical work and electromagnetic waves and heating, and right, so energy can be transferred from different types of stores to other types of stores, right? For example, sound waves, when you hear something, right, so energy is transferred from those waves, the vibrations, to our eardrums, right, or to a microphone in this case, like you're able to hear me, so the sound generated from my vocal cords through my mouth reaches the mic and then comes to you, to your ears, right? We gave the example of a heater or a boiler, so right, fossil fuels are burned to heat water, so again that is the purpose. And right, so there's different types of working involved, right, in energy transfers. So this is going to lead us into the topic of work. So different forms of work is involved in energy transfers, right? And examples of those, well, not examples, in summary, these are the ones, right? There's mechanical work, and that is under the action of a force. Then you have electrical work, which is caused by an electric current. You've got waves, right? So electromagnetic waves, sound waves, other waves. Right, what are other waves? For example, water waves, right? And so right, water is also used in hydroelectric power stations and heating. By conduction, convection, and radiation. And these are topics that we will cover. So we already talked about forces. Electrical working will come later in Unit 4. Waves will be dealt with in Unit 3, and heating is something that will be dealt in Unit 2. Right, so we will come across all of these in some more detail. And then they go on to list some energy transfers that highlight how the mechanical work or the heating takes place and causes the energy transfer. I'm not going into that, right, so you can read it. It's like just a list in the text. Now we come to measuring energy transfers and work. So any questions so far? Nothing really technical at all, just
No.
just information. So measuring energy transfers, and from here I'm going to talk about work. Alright, so work is a short chapter, separate chapter after the one we are talking about energy, but I will include it in this explanation. Right, so as you know, work is done when energy is transferred. And this is the scientific work, right? So it's not right me working right now because I'm giving you a class and you're working because you're studying scientifically in physics. That is not work. We're busy, yes, but because work has a very specific definition, right? And so work is a measure of the amount of energy transferred. So, right, and as I mentioned, right, both energy. Did I already write that down somewhere? Right. So I mentioned for energy, both energy and work are measured in joules. And so what is work? Right, it is the force applied to move an object a certain distance in the direction of the force. In the direction of the force applied. Just skip forward a bit. Yeah. And so how do we calculate work? Not work. Work done equals to force multiplied by the distance moved in the direction of the force. Right? In the direction of the force is important. Right? Or F multiplied by D. Right. So the unit of work is joules, as I mentioned, and a simple definition, right? How you get 1 joule of work is if you apply, if you move so 1 joule is when a force of 1 Newton is applied and moves an object through 1 meter. One Newton moves an object 1 meter. Right, so we know work equals to F into D, which is 1 times 1, which is 1 joule. Now, if for example you are applying a 50 Newton force to move something through 3 meters, and right, so what is the work done? Newton's force is applied to move an object 3 meters, and so that's 50 into 3, right, which gives you 150 joules. That is the amount of work done, right? And it's not just about horizontal movement, it can be vertical movement as well, right? So as long as the force applied in the direction of movement is the same, right, you have work being done. Clear?
Yes.
So right, an example of, as I mentioned, right, so technically you and I are not doing work at the moment because we're not moving. So right, if for example, right, there's a laborer or a worker who is carrying like 10 bricks, right, up 2 floors, so that may be I don't know, let's say let's just say 10 meters, right? He's carrying it up 10 meters, and so we know that carrying 10 bricks would require more force, right, as compared to a guy carrying 2 bricks at a time.
Yeah.
Right, the same height, 10 meters, and so right, carrying 2 bricks will utilize less force. So in one turn, right, who is doing more work?
The one with the
10 bricks.
10.
Right, now we're not talking about, oh, this guy is going to go up and down 5 times, and so we do that and it's going to come out to be equal. On paper, yes, perhaps the fact that he will have to go up and down 5 times will actually end up him utilizing more energy, he'll get more tired, perhaps because he's carrying less weight in each round, the other guy is carrying more weight in one round, and again, right, so those are technicalities, but right, on paper, the guy carrying 2 bricks in one round is compared to the guy carrying 10 bricks in one round, right, he's using more force and therefore he's doing more work.
Yeah.
Okay, any questions?
No.
And that was the topic of work, so we're done with that, right?
Okay.
Yeah, short topic. We still have time, so I'll carry on, that's all right?
Yeah.
Okay, so next is the principle of conservation of energy. And what does that state? It is one of the basic laws of physics, very basic. And it states that energy cannot be created nor destroyed, it is always conserved. Right, and so when we're talking about conservation, just like we talked about conservation of momentum yesterday, that means that the total energy of a system is always the same. Right, energy may be transferred from one store type to another. Right, but it's always right, and so this transfer includes energy loss. Right, and so energy lost is the energy that we were not able to utilize for whatever purpose we were doing that, right? So energy lost as light if we didn't want light, energy lost as heat, vibrations, movement perhaps, right? So whatever that we didn't want in the system but it is happening, it is not something that we can stop, that is energy loss. So including energy loss, the energy that is being utilized and whatever we're getting as a result, right, through work, it's always conserved in a system. And then that brings us to the fact that the total energy of the universe is conserved. Right, so just for as an example, right, we depend on the sun for light and heat, right? So whatever energy is being utilized, and you've got nuclear reactions going up over there, right? So we talked about nuclear energy. So the sun, right, is utilizing nuclear energy, and right, light and heat, there's sound as well. It's not coming to us, and that's a good thing, right? But right, because sound cannot travel through vacuum, so right, it's not reaching us. But the light and heat can reach us, and right, so we are utilizing that in different forms. We are storing that. Plants store it in form of chemical energy, and then it is eaten by other organisms, including ourselves, and then that energy is released through digestion, or it is stored by solar cells, right, as again chemical energy, and then utilized as electricity. And so whatever's going on, if you add that up and you look at the path that it's following, right, energy is conserved. It is just being transferred from one store to another. All right.
Yeah.
And on that note, right, what we want is to be careful about our choice of words when talking about energy, right? You do not say energy is produced, right? You do not say that.
Yeah.
Energy was created. Oh no, right? It is never created. Right? What you can say was energy was gained, right? Or energy was released. You could say that, right? So you have to be careful about the words that we use, especially in science in general, right? It's always better to use scientific terminology which sums up the concept that you're talking about, instead of going into details and spelling it out, unless you actually forgot the word that you wanted to use, and so you're trying to give the definition, and right. So, but particularly in the case of energy, be extra careful about your choice of words, right?
Yeah.
So energy is gained, energy is lost, energy is released, energy is stored, energy is transferred. It is not produced, it is not created, nothing like that. Then on this topic, right, they give again examples, right, of how energy is conserved. They talk about a hydroelectric power station, right, and so you've got a high level reservoir, as I mentioned, and then, right, the water is released downhill, and right, that goes to a water turbine. So gravitational potential energy moving to kinetic energy of the turbine, and that, right, goes to a generator, and so you've got, right, gravitational potential energy of water to kinetic energy of water to kinetic energy of turbine to different energy stores, right, as required by, right, consumers, let's say. So you're trying to generate electricity. Now what's happening at each step is that you've got heating and sound, and that is being lost at each step. And so taking that into consideration, right, and all the energy transfers, the total energy is conserved. Okay, so the lost energy is called non-useful transfers of energy. Right, all good?
Yep.
Okay, so the next topic, I will have to stop here, unfortunately.
Okay.
The next topic is gravitational, kinetic energy, gravitational potential energy. So they talk about that, they give the formula on how to calculate that. Then conservation of energy, so a practical situation, right? We talked about it theoretically, but then a practical situation and a calculation of how, right, you tackle with the situation and calculate the energy conversion, and then, right, go with, oh, how is it conserved. So we'll do that next class, and that will lead us to the end of the chapter. So that's definitely something we're covering. And then, right, there's a topic of energy resources. So I want that's right 1.7.3 in your O level book.
Yeah.
And right, let me just check which one it is in, yeah, 1.7.3 in the IGCSE as well. Right, for the most part they talk about efficiency later on, but what they talk about is renewable and non-renewable sources, right? So I will just mention that as we progress, but I want you to just read through it because it's just mostly information,
Okay.
right? So there's nothing technical or conceptual about energy resources, right? So I will just
Yeah.
briefly mention that when I come to that point, and then I will talk about energy efficiency and what efficiency is. Again, that's a very short topic, and then we'll move on to power. So do
Yeah.
read energy resources on your own, right?
Okay.
If there is anything, hopefully there isn't, but if there is anything that needs clarification, obviously you can ask.
All right.
All right, and so I will see you guys next class, inshallah.
Okay. Allah Hafiz.
Allah Hafiz.